Before we move on to temperature compensation, how strain gauges can be used for temperature compensation, I want to point out this table that's presented in your note packet. It shows how, depending on how you arrange the strain gauges within your Wheatstone bridge, you can determine how you can change the bridge constant value kappa, and it also tells you if it compensates for temperature or any type of mechanical compensation as well. Okay, so it gives you some examples for how they are arranged and those bridge constants. Okay, so it's a handy reference to have available to you if you're evaluating different types of Wheatstone bridges. All right, so temperature compensation is when you use um, is necessary in strain gauges, often because if you have a difference between your strain gauge and your mounted material, you can cause some strain due to that temperature change. In addition, you have current that's going through your strain gauge could slightly increase the heating of your strain gauge, and that increase in temperature could also affect the strain values that you're reading. So, to help account for this, we can use one of the following two setups, either by using an active gauge on the as far as the first resistor in both cases, but we can move the compensating gauge, which is basically on the same material and it's in the same environment as the strain gauge that's undergoing an applied load. All right, in this case, an axial load. All right, but it can be either placed in R2 or it can be placed within R3 here. All right, so those are our options. Now, either way in the equations, whether or not it's in R2 or in R3, our equation will simplify down to either the gauge factor over 4 times the difference between the strain in strain gauge 1 and the strain gauge and the difference in strain gauge 2, or it could be the difference between strain gauge 1 and strain gauge 3. All right. Now, in both cases, all right, if there's strain due to axial strain, which we'll call E axial, all right, that will only occur in the first gauge because it's the only one on the active gauge, while both materials will experience thermal strain ET. Okay, so if we plug in the value if we set E1 equal to E axial plus ET, all right, and E2 or E3 we set to be E thermal, all right, we get that the thermal components of our strains will get canceled out and we're left with just the output voltage being a function of that axial strain. Okay, so that's nice for us. All right, it's really nice, especially because we can use this method in the method that we introduced in the last video when we were talking about compensating for bending. We can compensate those two resistors if we had two strain gauges that were off, that were used as our, in that case what did we have here? We had two strain gauges, R1 and R4. We could have used compensating gauges for R2 and R3 to get rid of any thermal effects. So we could have a gauge that was both compensated for bending moment and for temperature. Okay, the so the way that you combine strain gauges can be very useful in trying to eliminate the effects that you're not interested in measuring.